Hello everybody. Till now we have learnt about how to design static CMOS circuits, and then we also learnt about dynamic and domino logic circuits. Today I am going to introduce you to a new logic design which is known as pass transistor logic. Okay, this again we discussed in the very first class that an NMOS transistor, when we use it as a switch, it can pass a perfect 0 but it cannot pass an perfect 1. Okay, the reason I will just revisit that idea here. Now if you have an NMOS here, you are applying a gate signal where A equal to VDD, that you are applying VDD to the gate. Okay, what happens if you are on the drain side, if you are applying VDD and you want the output node to be charged to VDD but it doesn't get charged to VDD, the maximum voltage which would be available will be VDD minus VTN. Okay, so what is the reason? Now since this is an NMOS, okay, the majority carrier here are electrons. So now from VDD the charge has to come here. That means the positive charge will move like this from the left to right. So whereas the electrons will move from right to left, right? So that is why since the electrons are going to move into this device, so this from this terminal we call this as source and we call this as drain. Now if you see here, this becomes so this becomes VGS. Okay, now we also know that for this transistor to remain on, VGS has to be greater than VTN. So when we are trying to take this node voltage to VDD, we are applying VDD here and switching on this transistor by applying VDD here. What happens is this capacitor, the output node capacitor, slowly keeps getting charged, and the moment it reaches VDD minus VTN, the gate source voltage will be VDD minus of VDD minus VTN. That means it becomes VTN out here, and it cannot go further high, because once it goes further beyond VTT minus VTN, then gate source voltage will become less than VTN and this transistor gets switched off. So that is the reason NMOS cannot transmit an perfect 1. Okay, so the maximum voltage when you are using NMOS as a switch is VDD minus VTN. Whereas when we have to transmit a 0, now in this case you are applying 0, you are assuming this output node is already charged to 1. Now the positive current will flow like this, right, from the drain to the source, which is indicated. We are calling this source because now a positive charge is going to flow here, negative is going to flow in the opposite direction. So that is the reason we call now this as source here. Here we are calling it source here because positive charge was coming like this and negative electrons were moving like this. So here now the electrons are going to move like this, right? So whatever charge, positive charge is accumulated here, that has to get discharged. So this becomes now the source. Now if you see here, this is 0, permanently 0, this is permanently VDD. So irrespective of the drain voltage, this transistor will remain on. So that means this capacitance will get totally discharged to 0 because VDS will come to 0. So VGS is continuously going to remain VDD in this case, which is higher than VTN. So that is the reason NMOS is a perfect 0. It can pass perfect 0 but not 1. So the reverse is true for the PMOS. In this case, if I have a VDD here, this is a PMOS. Now to switch on an PMOS, we know that we need to give 0 to the gate voltage. Now when I give 0 here, now the positive ion is going to move like this, right? So that is why we call this as source. So the output can get charged till VDD because VGS continues to remain, SG in this case continues to remain VDD because this is VDD, this is 0 continuously. So this will continuously, this PMOS will continuously remain on, and hence this can go up to VDD. There is no problem with that. Okay, but with the PMOS, if I am trying to transmit a 0, if this is 0, now this becomes source because now positive ions are going to come like this. This becomes source. In this case, now again when the output reaches VTP, okay, VTP, mod VTP you can call that, when it reaches VTP, then this transistor will get switched off. right? Because now here this is 0, this is VTP, so VSG is VTP, so there can no this PMOS, if it is going to fall below VTP, then this PMOS is going to get switched off. So that is the reason it cannot transmit a perfect 0. There will be a residual voltage of VTP. Okay, for one it will get charged to VDD. For an NMOS, the maximum voltage which can go is VDD minus VTN, whereas perfect 0. So this is just the opposite which happens. So when we make there is something known as complementary pass transistor logic. So in this case we use a combination of NMOS and PMOS in parallel. So you give enable to the NMOS and enable bar to the PMOS. So they work in parallel. So whenever the enable signal goes high, this NMOS as well as this PMOS both are switched on simultaneously. So this will ensure that both zeros and ones are transmitted properly. Okay, so this is one method of to get rail to rail output. Okay, so this is the general symbol for a complementary pass transistor which is generally used. Okay, now let's see how to design a few gates using pass transistor logic. So the first implementation is F is equal to AB. Okay, so you might think if I use an NMOS out here and if I put a here, a B here, so when A is 1, B is 1, I will get output 1, right? So that only one transistor would be sufficient, you might think, but that is not the case, because what happens when B is equal to 0? Okay, you have to cater even for that contingency, right? So when B is equal to 0, what happens to F? So B is equal to 0, F is 0. So I put one more gate here, I put B dash and is equal to 0. So the design is going to be like that. You take one of the variables, and there is, for one of the variables, like in this case B, there are two possible combinations. One is when B is equal to 1, then when F is equal to A in that case, so I put A here, and now when B is equal to 0, F is equal to 0, so I put 0 here. Okay, so F is equal to AB. So obviously this particular circuit will have a drawback that because you are using NMOS out here, so the output will not be VDD, it will be VDD minus VTN. Whenever for 0 it's not a problem. So when A and B both are 1, the total, so you will have to use one level restore here. Okay, you have to do something about it. Similarly, if I have to design F is equal to A or B, now if B is equal to 0, right, and if B is equal to 0, F is equal to A, so I put B bar here and A here, and when B is equal to 1, F becomes 1, so I put 1 here, right? So this is how A or B can be realized. Now these pass transistor logics, they have certain advantages over the static design. One is negligible static dissipation. Excuse me, right? So if you see the CMOS circuit, so there will be a path between VDD and ground because of the leakage currents which are there in the PMOS and NMOS, even though they are switched off, right? Here that is not the case, so it will be much lesser dynamic consumption and short circuit switching loss. So these losses are not there in the pass transistor circuits. Okay, so they only just pass the logic levels. So you will find the capacitances here, the circuits are pretty simple, so the total net capacitance is less, and hence the switching losses are less. Also the short circuit currents, like we saw there will be short circuit currents when the input is transiting from 0 to 1, there is a path available from VDD to ground. So those kind of things are not there in the pass transistor logic. So this is much efficient than the static CMOS circuit. Okay, so let's first design one circuit, and once you are comfortable with one particular circuit, you will be able to design any circuit with pass transistor. So we are going to take an example of full adder. So this is the expression for sum, right? Sum is an A B bar C in bar plus an A bar B C in bar plus A bar B bar C in plus A B C, right? These are the 4 different conditions for which the sum will be 1, right? Now so first we are going to take C in for this is the sum output available here. Okay. Now for C in is equal to 0, you will see this gate will be enabled, right? So if you see here, for C in is equal to 0, and then I have A equal to 0. So A equal to 0, this will be enabled. So for C in is equal to 0, A is equal to 0, it's B. So sum is equal to B. So B will flow from here. A is equal to 0, C in is equal to 0. I get a sum out here. Similarly, for the next condition, for C in is equal to 0 and A equal to 1, sum is equal to B bar. So C in is equal to 0, A equal to 1, I get a B bar out here, right? Now the third condition is C in is equal to 1 and A is equal to 0. So C in is equal to 1 means this gate is going to get enabled, and then A equal to 0, it is for 1 this is coming here. For A equal to 0, A bar will get activated. So I have B bar here. So I have a B bar here. And then the last condition is C in 1, A is equal to 1, sum is equal to B. So C in 1, A equal to 1, I get B. Okay, so this is how all the four different conditions are met. Here you have two gates out here, C in and C in bar here. For each of that, I can have A and A bar, two different conditions. So that is how. Now here similarly, this expression has been written for sum. You need to write an expression for sum bar also, and then you have this is sum bar coming here, right? So this is sum bar. This is sum is generated here, and you put an inverter, you get a sum bar here. Now you are using a sum bar here, and you are taking sum here. So this sum bar. So the way we have written expression for sum, you need to write it for sum bar, and then you got to put these conditions. And C in is equal to 0, C in equal to 1, A equal to 0, A equal to 1, A is equal to 0, A equal to 1, and then accordingly design these circuits for sum bar also. Now if you see here, why are we using these two PMOS? That is to restore the like we know this is not a perfect one, since we are using NMOS out here, right? And we are also generating, like we have generated sum here, we are generating sum bar here. Okay, so whenever sum is 1, sum bar will be 0. So I use a PMOS circuit here. Okay, so this becomes if sum is 1, it will not be a perfect one, but sum bar will be 0. So that 0 is given to a PMOS. So it will since this PMOS will be switched on, and this will get charged to full VDD. Okay, so that this is a level, like we learnt in the dynamic circuit in the last class about a keeper transistor. So you can call this as a keeper transistor here also. Similarly, this is generating a sum bar here. Okay, once it is generating a sum bar here, okay, this is a keeper circuit, so you are feeding it from the sum input. Okay, so here these two signals are there. This acts like a buffer. So you have in two inverters out here, so this will isolate this particular circuit. Now this can have a good current carrying capacity. So I am this is sum bar, and this will be sum, this is sum and sum bar. So these two signals will be generated. Okay, generally for a pass transistor circuit, since again you are expecting one more pass transistor circuit in the next stage, so we are generating both sum and sum bar here. Like here there is a requirement of all the CI and C bar is required, right? So similarly for the next stage also sum and sum bar might be required. So that is why whenever we talk about pass transistor logic, we generate both sum and sum bar. If there is a specific requirement of generating only sum also, then we can do away with this particular circuit. Okay, we can do away with, or we can just have only the bottom branch, and this particular thing can be driven from here also. Okay, you can do that also. Right, so now you have similarly that sum was circuit was designed, you can do an carry also. Okay, since this is the expression for carry, now if you see, if you put a carry in is equal to 0, so this become AB or B or C, right? So it becomes just an A bar C. So if you see here, this is carry here, right? So this is carry bar, so this is carry here. For C in is equal to 0, so you have an A or B. So when sorry, it will become an A or B, right? So you will find here So when carry in is equal to when carry in is equal to 0, it will become this is 0, carry out will be A and B. So 0 means carry bar if you come here. So A and B, so A bar it is 0, so this is A and B, right? This is A and B. Similarly, when carry out when C in is equal to 1, right, this will become 1, this will become 1, this is A and B, then or A or B, so it will become A or B. So if you see here, when C in is equal to 1, this is nothing but A or B, right? So when A is 1, it is 1, and A is equal to 0, it is B. So this becomes A or B. Similarly, for we have to do the same thing. If you have to make C out bar here, right? So we write an expression for C out bar. So here this is C out, this is C out. So you write a C out bar, and then we take two conditions. For C in is equal to 0, C out bar will become, right? And so for C out bar in this expression, we put an C in is equal to 0. So this is going to be 1, this is going to be 1 out here, right? So 1 or and 1 or, so this will vanish, only this will remain. So for A is equal to 0, you will get C out is equal to 1. For A equal to 1, C out is equal to B dash, you will get, right? So if you see here, C, this is C in bar out here. For and then for C in is equal to 0, right? For C in is equal to 0, this is the path here, right? For C in is equal to 0, right? For A is equal to 0, A equal to 0, it is 1, and for A is equal to 1, it is B bar. A is equal to 1. So this is the circuit. For C in is equal to 0, for A is equal to 1, it is B bar. For A equal to 0, it is 1. So similarly, this you get this expression again for A equal to 0, that is when C in is equal to 1. So this path. So for A is equal to 0, right? Now for A is equal to, C out is B. So A is equal to 0 means A bar, it is B bar out here. And similarly, for A is equal to 1, C out is equal to 0. So A equal to 1, C out is equal to 0. So this is how we do the design. So for pass transistor logic, the technique is simple. First you write the expression for C out bar, and then the first set of gates. Now in this particular example, I have taken C in as the first variable. Okay, you can take it A also, you can take it B also. So accordingly the gate gets modified. Not necessarily you will always have to start with C in. Okay, so here I have taken C in is equal to 0, C in is equal to 1. So I get two different conditions. So there are two different conditions, and then from each of these two conditions there are again two conditions for the next variable, and then whatever is the expression you are getting by simplifying, by putting these values, C in is equal to 0, A is equal to 0, you whatever expression you get, that you are going to feed in here, right? So accordingly these kind of pass transistor logic circuits can be designed. So let me now show you a demo. Now this is again a pass transistor logic circuit, full adder, which we have designed using the 180 nanometer technology files, which we have been doing till now. I have explained how to import these in the very first lecture. Okay, and now if you see, the same circuit which we discussed has been implemented in pass transistor logic. So one thing which we need to take care is everywhere wherever NMOS is used, the body is grounded here, and wherever PMOS has been used, okay, there the body is been set to VDD, right? So this is known as the level restorer PMOS, okay, or the keeper PMOS, keeper PMOS for the sum, and two for the carry, which we have used. Okay, so I have used three sources, and then the only thing is this is the source. So 1.8 and 0, that is A bar is exactly same. Okay, the frequency rise time, it has to be exactly same. Only thing is this is 0 and 1.8, so I get an A bar. So for pass transistor circuits you will require A bar, B bar, and C bar. Okay, so how to generate? So you will have to, for each of those signals, for each of the variables, you will require the complementary also, and you can generate the complementary just by swapping the initial and the on values. Okay, so once you have done that, so if you I can plot A, B and C, and I can plot some bar. Okay, and let me plot the sum itself and the carry, right? So so this is A, this is B, this is C, right? This is sum, and if you see sum bar is just the supplementary, the complementary signal is also available. Similarly, you have carry bar also. So you can see 0 0 0 is giving us 0 0, 0 0 1 is giving us an 1 0. The sum is the pink one, so it is gone 1 here. 0 1 0 is again giving. So whenever we have two ones, the sum is going 0, sum bar is going 1, and carry is going 1 here, right? So and in the last case where all there are three ones, the sum is 1 and the carry is 1 and sum bar is 0. So this is how this is the circuit which you can try it of your own. Okay, now we have learned a little bit about pass transistor logic. So in the same manner, I have demonstrated how to implement a full adder. You can go ahead and design multiplexers and multiplexer mux based, because mux also you can go through the literature, you will find several circuits where mux can be easily implemented using pass transistor switches, so and decoders. So you can try out on a few circuits based on mux and decoders. In case you have any problem or if you are getting stuck, feel free to get in touch with me. Okay, thanks a lot.